In mathematics, a continued fraction is an expression obtained through an iterative process of representing a number as the sum of its integer part and the reciprocal of another number, then writing this other number as the sum of its integer part and another reciprocal, and so on. In a finite continued fraction, the iteration, recursion, is terminated after finitely many steps by using an integer in lieu of another continued fraction. In contrast, an infinite continued fraction is an infinite expression. In either case, all integers in the sequence, other than the first, must be positive. The integers I are called the coefficients or terms of the continued fraction. Continued fractions have a number of remarkable properties related to the Euclidean algorithm for integers or real numbers. Every rational number Q has two closely related expressions as a finite continued fraction, whose coefficients I can be determined by applying the Euclidean algorithm to. The numerical value of an infinite continued fraction will be irrational. It is defined from its infinite sequence of integers as the limit of a sequence of values for finite continued fractions. Each finite continued fraction of the sequence is obtained by using a finite prefix of the infinite continued fractions defining sequence of integers. Moreover, every irrational number alpha is the value of a unique infinite continued fraction, whose coefficients can be found using the non-terminating version of the Euclidean algorithm applied to the incommensurable values alpha and 1. This way of expressing real numbers is called the continued fraction representation. It is generally assumed that the numerator of all of the fractions is 1. If arbitrary values and/or functions are used in place of one or more of the numerators or the integers in the denominators, the resulting expression is a generalized continued fraction. When it is necessary to distinguish the first form from generalized continued fractions, the former may be called a simple or regular continued fraction, or said to be in canonical form. The term continued fraction may also refer to representations of rational functions, arising in their analytic theory. For this use of the term, see Padé approximation and Chebyshev rational functions. Motivation and notation. Consider a typical rational number 415/93, which is around 4.4624. As a first approximation, start with 4, which is the integer part. 415/93 equals 4 plus 43/93. Note that the fractional part is the reciprocal of 93/43, which is about 2.1628. Use the integer part, 2, as an approximation for the reciprocal, to get a second approximation of 4 plus 1/2 equals 4.5, 93/43 equals 2 plus 7/43. The remaining fractional part, 7/43, is the reciprocal of 43/7, and 43/7 is around 6.1429. Use 6 as an approximation for this to get 2 plus 1/6 as an approximation for 93/43, and 4 plus 1/2 plus 1/6, about 4.4615. As the third approximation, 43/7 equals 6 plus 1/7. Finally, the fractional part, 1/7, is the reciprocal of 7, so its approximation in this scheme, 7, is exact and produces the exact expression 4 plus 1/2 plus 1/6 plus for 415/93. This expression is called the continued fraction representation of the number. Dropping some of the less essential parts of the expression 4 plus 1/2 plus 1/6 plus gives the abbreviated notation 415/93 equals 4, 2, 6, 7. Note that it is customary to replace only the first comma by a semicolon. Some older textbooks use all commas in the tuple, e.g., 4, 2, 6, 7. If the starting number is rational, then this process exactly parallels the Euclidean algorithm. In particular, it must terminate and produce a finite continued fraction representation of the number. If the starting number is irrational, then the process continues indefinitely. This produces a sequence of approximations, all of which are rational numbers, and these converge to the starting number as a limit. This is the continued fraction representation of the number. Examples of continued fraction representations of irrational numbers are square root 19 equals 4, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8. The pattern repeats indefinitely with a period of 6. Equals 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8. The pattern repeats indefinitely with a period of 3 except that 2 is added to one of the terms in each cycle. Pi equals 3, 7, 15, 1292, 1, 1, 1, 2, 1, 3, 1. The terms in this representation are apparently random. Equals 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. The golden ratio, the most difficult irrational number to approximate rationally. C. A property of the golden ratio phi. Continued fractions are, in some ways, more mathematically natural representations of a real number than other representations such as decimal representations, and they have several desirable properties. The continued fraction representation for a rational number is finite and only rational numbers have finite representations. In contrast, the decimal representation of a rational number may be finite, for example, 137 1/1600 equals 0.085625, or infinite with a repeating cycle, for example 4/27 equals 0.148148148. Every rational number has an essentially unique continued fraction representation. Each rational can be represented in exactly two ways, since a0, a1, and -1, and equals a0, a1, and -1, 1. Usually the first, shorter one is chosen as the canonical representation. The continued fraction representation of an irrational number is unique. The real numbers whose continued fraction eventually repeats are precisely the quadratic irrationals. For example, the repeating continued fraction 1, 1, 1, 1 is the golden ratio, and the repeating continued fraction 1, 2, 2, 2 is the square root of 2. In contrast, the decimal representations of quadratic irrationals are apparently random. The square roots of all integers that are not perfect squares are quadratic irrationals, hence are unique periodic continued fractions. The successive approximations generated in finding the continued fraction representation of a number, i.e., by truncating the continued fraction representation, are in a certain sense the best possible. Basic formula. A continued fraction is an expression of the form where I and bi are either rational numbers, real numbers, or complex numbers. If bi equals 1 for all I, the expression is called a simple continued fraction. If the expression contains a finite number of terms, it is called a finite continued fraction. If the expression contains an infinite number of terms, it is called an infinite continued fraction. Thus, all of the following illustrate valid finite simple continued fractions. Calculating continued fraction representations. Consider a real number r. Let I equals r be the integer part of r and let f equals r minus I be the fractional part of r. Then the continued fraction representation of r is I, a1, a2, where a1, a2 is a continued fraction representation of 1, f. To calculate a continued fraction representation of a number r, write down the integer part of r. Subtract this integer part from r. If the difference is 0, stop. Otherwise find the reciprocal of the difference and repeat. The procedure will hold if and only if r is rational. This process can be efficiently implemented using the Euclidean algorithm when the number is rational. The number 3.245 can also be represented by the continued fraction expansion 3, 4, 12, 3, 1. Refer to finite continued continued fractions below. Notations for continued fractions. The integers a0, a1 etc. are called the coefficients or terms of the continued fraction. One can abbreviate the continued fraction in the notation of Carl Friedrich Gauss or in the notation of Pringsheimers, or in another related notation, as sometimes angle brackets are used, like this. The semicolon in the square and angle bracket notations is sometimes replaced by a comma. One may also define infinite simple continued fractions as limits. This limit exists for any choice of a0 and positive integers a1, a2. Finite continued fractions. Every finite continued fraction represents a rational number, and every rational number can be represented in precisely two different ways as a finite continued fraction, with the conditions that the first coefficient is an integer and other coefficients being positive integers. These two representations agree except in their final terms. In the longer representation, the final term in the continued fraction is 1, the shorter representation drops the final 1, but increases the new final term by 1. The final element in the short representation is therefore always greater than 1, if present. In symbols, a0, a1, a2, and -1, and 1 equals a0, a1, a2, and -1, and +1. a0, 1 equals a0 plus 1. For example, 2.25 equals 2 plus 1/4 equals 2, 4 equals 2 plus 1/3 plus 1 over 1 equals 2, 3, 1, minus 4.2 equals -5 plus 4/5 equals -5 plus 1 over 1 plus 1/4 equals -5, 1, 4 equals -5 plus 1 over 1 plus 1/3 plus 1 over 1 equals -5, 1, 3, 1. Continued fractions of reciprocals. The continued fraction representations of a positive rational number and its reciprocal are identical except for a shift one place left or right, depending on whether the number is less than or greater than 1 respectively. In other words, the numbers represented by a0, a1, a2, and 0, a0, a1, are reciprocals. This is because if a is an integer, then if x less than 1, then x equals 0 plus 1, a plus 1, b and 1, x equals a plus 1, b, and if x greater than 1, then x equals a plus 1, b and 1, x equals 0 plus 1, a plus 1, b, with the last number that generates the remainder of the continued fraction being the same for both x and its reciprocal. For example, 2.25 equals 9/4 equals 2, 4, 1, 2.25 equals 4/9 equals 0, 2, 4. Infinite continued fractions. Every infinite continued fraction is irrational, and every irrational number can be represented in precisely one way as an infinite continued fraction. An infinite continued fraction representation for an irrational number is useful because its initial segments provide rational approximations to the number. These rational numbers are called the convergence of the continued fraction. The larger a term is in the continued fraction, the closer the corresponding convergent is to the irrational number being approximated. Numbers like pi have occasional large terms in their continued fraction, which makes them easy to approximate with rational numbers. Other numbers like e have only small terms early in their continued fraction, which makes them more difficult to approximate rationally. The golden ratio has terms equal to 1 everywhere, the smallest values possible, which makes the most difficult number to approximate rationally. In this sense, therefore, it is the most irrational of all irrational numbers. Even-numbered convergents are smaller than the original number, while odd-numbered ones are larger. For a continued fraction, a0, a1, a2, the first four convergents are 0 over 1, a1 a0 plus 1, a1, a2 plus a0, a2 a1 plus 1, a3 plus a0, plus a3 plus a1 in words. The numerator of the third convergent is formed by multiplying the numerator of the second convergent by the third quotient. and adding the numerator of the first convergent. The denominators are formed similarly. Therefore, each convergent can be expressed explicitly in terms of the continued fraction as the ratio of certain multivariate polynomials called continuants. If successive convergents are found, with numerators h1, h2, and denominators k1, k2, then the relevant recursive relation is hn equals an hn minus 1 plus hn minus 2, knots equals an kn minus 1 plus knots minus 2. The successive convergents are given by the formula hn knots equals an hn minus 1 plus hn minus 2, an kn minus 1 plus knots minus 2. Thus, to incorporate a new term into a rational approximation, only the two previous convergents are necessary. The initial convergence are 0 over 1 and 1/0. For example, here are the convergents for 0, 1, 5, 2, 2. When using the Babylonian method to generate successive approximations to the square root of an integer, if one starts with the lowest integer as first approximant, the rationals generated all appear in the list of convergents for the continued fraction. Specifically, the approximants will appear on the convergence list in positions 0, 1, 3, 7, 15, 2k-1. For example, the continued fraction expansion for square root 3 is 1, 1, 2, 1, 2, 1, 2, 1, 2. Comparing the convergence with the approximants derived from the Babylonian method, x0 equals 1 over 1, x1 equals 1/2 equals 2 over 1 equals 2 by 2 equals 1/2 equals 7/4, x3 equals 1/2 equals 97/56. Properties of infinite continued fractions. Their space is a topological space on infinite sequences of natural numbers. The infinite continued fraction provides a homeomorphism from bare space to the real numbers. The infinite continued fraction also provides a map between the quadratic irrationals and the dyadic rationals, and from other irrationals to the set of infinite strings of binary numbers. This map is called the Minkowski question mark function. The mapping has interesting self-similar fractal properties. These are given by the modular group, which is the subgroup of Mobius transformations having integer values in the transform. Roughly speaking, continued fraction convergence can be taken to be Mobius transformations acting on the upper half plane. This is what leads to the fractal self-symmetry. Some useful theorems. If A0, A1, A2 is an infinite sequence of positive integers, define the sequences Hn and knots recursively. Theorem 1. For any positive real number Z. Theorem 2. The convergence of A0, A1, A2 are given by Theorem 3. If the nth convergent to a continued fraction is Hn knots, then Corollary 1. Each convergent is in its lowest terms. Corollary 2. The difference between successive convergents is a fraction whose numerator is unity. Corollary 3. The continued fraction is equivalent to a series of alternating terms. Corollary 4. The matrix has determinant plus or minus 1, and thus belongs to the group of 2 times 2 unimodular matrices GL. Theorem 4. Each convergent is nearer to a subsequent convergent than any preceding convergent is. In symbols, if the nth convergent is taken to be A0, A1, and equals xn, then for all r less than s less than n. Corollary 1. The even convergents continually increase, but are always less than xn. Corollary 2. The odd convergents continually decrease, but are always greater than xn. Theorem 5. Corollary 1. Any convergent is nearer to the continued fraction than any other fraction whose denominator is less than that of the convergent. Corollary 2. Any convergent which immediately precedes a large quotient is a near approximation to the continued fraction. Semi-convergence. If Hn-1, knots -1, Hn, knots are successive convergents. then any fraction of the form hn-1 plus un nox -1 plus akn, where a is a non-negative integer and the numerators and denominators are between the n and n plus 1 terms inclusive, are called semi-convergence, secondary convergence, or intermediate fractions. Often the term is taken to mean that being a semi-convergent excludes the possibility of being a convergent, rather than that a convergent is a kind of semi-convergent. The semi-convergence to the continued fraction expansion of a real number x include all the rational approximations, which are better than any approximation with a smaller denominator. Another useful property is that consecutive semi-convergents A, B and C, D are such that AD minus BC equals plus or minus 1. Best rational approximations. A best rational approximation to a real number x is a rational number n, d greater than 0, that is closer to x than any approximation with a smaller or equal denominator. The simple continued fraction for x generates all of the best rational approximations for x according to 3 rules. Truncate the continued fraction, and possibly reduce its last term. The reduced term cannot have less than half its original value. If the final term is even, half its value is admissible only if the corresponding semi-convergent is better than the previous convergent. For example, 0.84375 has continued fraction 0.1522. Here are all of its best rational approximations. The strictly monotonic increase in the denominators as additional terms are included permits an algorithm to impose a limit, either on size of denominator or closeness of approximation. The half rule mentioned above is that when ac is even, the half term ac2 is admissible if and only if x minus a0, a1, ac minus 1 greater than x minus a0, a1, ac minus 1, ac2. This is equivalent to ac minus 1, a1 greater than ac plus 1. The convergence to x are best approximations in an even stronger sense. N, D is a convergent for Ex if and only if dx minus n is the least relative error among all approximations M, C with CD, that is, we have dx minus n less than Cx minus M, so long as a C less than D. Best rational within an interval A rational that falls within the interval for 0 less than x less than y, can be found with the continued fractions for x and y. When both x and y are irrational and x equals a0, a1, a2, ac minus 1, ac plus 1, y equals a0, a1, a2, ac minus 1, bk plus 1. Where x and y have identical continued fraction expansions up through ac minus 1. A rational that falls within the interval is given by the finite continued fraction z equals a0, a1, a2, ac minus 1, min plus 1. This rational will be best in that no other rational in will have a smaller numerator or a smaller denominator. If x is rational, it will have two continued fraction representations that are finite, x1 and x2. And similarly a rational y will have two representations, y1 and y2. The coefficients beyond the last in any of these representations should be interpreted as plus infinity, and the best rational will be one of z, or z. For example, the decimal representation 3.1416 could be rounded from any number in the interval 3.14155, 3.14165. The continued fraction representations are 3.14155 and 3.14165 of 3.14155 equals 3, 7, 15, 2, 7, 1, 4, 1, 1 equals 3, 7, 15, 2, 7, 1, 4, 2, 3.14165 equals 3, 7, 16, 1, 3, 4, 2, 3, 1 equals 3, 7, 16, 1, 3, 4, 2, 4, and the best rational between these two is 3, 7, 16 equals 355 113 equals 3.1415929. Thus, in some sense, 355 113 is the best rational number corresponding to the rounded decimal number 3.1416. Interval for a convergent irrational number, which can be expressed as finite continued fraction in two ways, z equals a0, a1, ac minus 1, ac 1 equals a0, a1, ac minus 1, ac plus 1, will be one of the convergents for the continued fraction expansion of a number, if and only if the number is strictly between x equals a0, a1, ac minus 1, ac 2, and y equals a0, a1, ac minus 1. ac plus 2. Note that the numbers x and y are formed by incrementing the last coefficient in the two representations for z, and that x less than y when k is even, and x greater than y when k is odd. For example, the number 355 113 has the continued fraction representations 355 113 equals 3, 7, 15, 1 equals 3, 7, 16, and thus 355 113 is a convergent of any number strictly between comparison of continued fractions. Consider x equals a0, a1, and y equals b0, b1. If k is the smallest index for which ac is unequal to bk, then x less than y if k less than 0 and y less than x otherwise. If there is no such k, but one expansion is shorter than the other, say x equals a0, a1, and y equals b0, b1, bn plus 1, with I equals by for 0 in, then x less than y if n is even and y less than x if n is odd.